Assalamu alaikum everyone. Myself Abrar, ID 2200212334. I am one of the members of the Team BitsQ under the supervision of Nadim Mohammed sir. My teammates consist of Saif Muhammad, ID 22002117, Talha Ahmed, ID 2200213350, Zabid Fardin, ID 2200213005, Mashiat Rohan Prinon, ID 2200212226, Abrar Rohan, ID 2200213555, and last but not the least, Sakib, ID 2200211120. We are thrilled to accompany you throughout this detailed presentation of the Snake Ladder game project that was assigned to us under the course code 434308. We dearly hope you will find our project, into which we all put our heart and soul worth of effort, that are fascinating while meeting all of your expectations. So without further ado, let us begin.
I'm going to give the overview of the Snake Ladder game now. For the game, first we have the board module, which consists of some LEDs. The LEDs represents the player position, the ladder position, and the snake position. From the module part, we have the player position decoder module for both player 1 and player 2. This module represents the player current position in the board module. Then we have the ladder position decoder. Here, the user manually inputs the ladder start and the ladder length. After some calculation, we represent the ladder head or the ladder top and the ladder bottom at the board module. Similarly, you have snake position decoder, where here the user manually inputs the snake start and snake length. After some calculation, we represent the snake head and snake tail at the board module. Then we have snake ladder logic module. Here the main calculation of our game happens. We get the ladder start, ladder length, ladder snake start, snake length, and the player current position, also the dice input. We first take the player current position and the dice input and add them and get the temporary position of the player. Then we check if the temporary position of the player is at the bottom of a ladder or at the head of a snake. If the temporary position of the player is at the bottom of the ladder, the next position of the player will be at the top of the ladder. Or if the temporary position of the player is at the top of the or head of the snake, the next position of the player will be at the bottom of the snake. So we check that and send the output to the game memory. Then we have the dice module. Here we have a push button. While we push and hold the button, we get a number that continuously changes. After we release the push button, the number gets a fixed value and that is sent to the snake ladder logic module. We also have a debouncer circuit in the dice module. This removes the mechanical error that can happen while the push button is pushed. Then we have the player selector module. This player selector module selects the current player that is active in our game. This happens automatically in our game. Initially, player 1 is selected for our game, and after we press the dice button, the player 2 is automatically selected. Then we have game memory. In game memory, the current position of the player are stored. After we get the next position of a player for the selected player from the snake ladder logic module, the game memory updates that position and sends this to the player position decoder, and thus it is updated at the board module. Then we have the reset module. The reset module resets the whole game. When we have a push button for the reset module, if we push the reset button, the whole game is resetted and we get the position of the player at the 0, and the ladder and the snake position remains same. Also, the current selected player is player 1. Also, we have a high frequency memory clock module. This is used for any kind of clock pulse in our game. We used this in the dice module, in the game memory. Anywhere we used any flip-flop, we needed that clock pulse, so those clock pulses are taken from the high frequency memory module. Finally, we have the winner module. The winner module checks if the player current position for both player 1 or 2 is at the last position of the game. If it is true that the player current position is at the last position of the game, that player wins the game, and it represents that by lighting up an LED for the player.
This is the snake position decoder module along with the PCB. So we take the 4-bit snake's head position and the 4-bit snake's length from the player's cell. Then we If we go into the child sheet, then we use a 4 to 16 decoder to get the signal of the corresponding position for the snake set from these inputs to this decoder. Next, we use a 4-bit full adder as a subtractor, this adder as a subtractor to subtract the snake's length from its head's position. So these are the length input and these are the head input, head position input of the snake from the players. And now to make this adder function like a subtractor, we invert the snake's length inputs from the players using 4 NOT gates here. Then we input the result into this decoder. From this adder, we subtract. We use this adder as a subtractor. We get the output here, and then we use this 4 to 16 decoder to get the position of snake's tail. Finally, we use 16 AND gates to channel the 32 output bits to 16 output bits, because in the board module we have space to input only 16 bits, not 32 bits. Additionally, if even one of the corresponding 2 out bits from the 2 decoders here turns to 0, then the LED of the corresponding position lights up, like in this case. And these are some connectors and terminal blocks as well as some bus capacitors we have used for a PCB layout, which is right here. And if we see it in the 3D visualizer, then we have this PCB board here. So yeah, that's about it for the snake position decoder. Thank you. So this is the ladder position decoder module. Here we have 2 connectors. This ladder bottom connector receives the 4-bit ladder's position from the player, and this connector receives the 4-bit ladder's length from the players. If we go into this child sheet, then we'll see that using this 4 to 16 decoder, we obtain the ladder's bottom position, and through this 4-bit full adder, we obtain the ladder's top position by adding the ladder length with the ladder bottom position. Then we use this 4 to 16 decoder again to get the corresponding signal for the ladder's top position. Finally, we use the 16 AND gates because we have here, as we know that in the board module we have space to input only 16 bits, not 32 bits. Again, additionally, if one of the corresponding 2 output bits from these 2 decoders turn to 0, then the LED of the corresponding position of the ladder will light up. So yes, this is how it basically operates. Then we have some bypass capacitors, a terminal block here, some other connectors there, which will help us in the PCB design. And for talking about the PCB, we have this PCB here, a pretty simple one. And then if we see it in the 3D visualizer, we have this simple PCB, this board here, then we will use in the game. So yes, this is how this ladder position decoder works. Thank you.
It is our board module. It is basically a 4x4 grid composed of 16 cells. Now each cell composed of 4 different types of LEDs: the red LED, the blue LED, the yellow LED, and the green LED. The red LED represents the position of player 1, the blue LED represents the position of player 2, and the yellow LED either represents the snake tail or snake head, and the green LED either represents the ladder bottom or the ladder top. Now if this LED get lit up, we know that the player on is in the position, in the cell on or in the position on. And if this LED gets lit up, we know that the player on's position is now in the cell 3 or position 3. Same goes for the LED blue for player 2 actually. And for the snake, if this LED and this LED get lit up, we know that this is the snake tail and this is the snake head. And the same goes for the ladder. If this LED and this LED get lit up, we know that this is the ladder bottom and this is the ladder top. And if that is exactly on yellow LED in the whole grid get lit up, we know that the snake tail and the snake head are in the same position. And same goes for the ladder. If we exactly on green LED gets lit up in the whole grid, we know that the ladder top and the ladder bottom is in the same position. And another thing, how do you calculate the resistance value? We calculated it in the tech shop video. We saw that the LED's voltage rating and the maximum current rating. We maybe saw that the LED's voltage rating may be 1.9 voltage. So we took the maximum current also 10 milliampere. We took the maximum current and the maximum voltage. We know that in this whole region there will be 5 volt. The voltage will be 5. So 5 minus 1.9 voltage, the result we get, we just divided the result with the 10 milliampere. That's how we get the 250 ohm value. Same for the whole, for every LEDs. So this is it, and this is the PCB. This is the PCB of the board module. If we here. This is the PCB.
So this is the player position decoder module. As you can see, there are two identical decoders here for each player. This is for player 1 and this is for player 2. So we can just discuss about one player. Let's say in this case we'll just discuss about player 1. So here we take the 4-bit input for each player's updated position from the memory module through these inputs. In the sub-circuit, here if we see, we input each player's 4-bit position value into this 4 to 16 decoder to get the corresponding signal for that player's position in an active low configuration. So this has been also repeated for player 2 as well, as you can see here. So, and here are some connectors, a terminal block, along with two bypass capacitors here. Here are some connectors as well, which will aid us in the PCB design. And here is the PCB design, the simple one that is. And if we might see in this in a 3D visualizer. So yeah, this is about the player position decoder. So yeah, thank you. Here we have the snake ladder logic module. As you can see, here are 5 sets of inputs here. The first set of inputs, these connectors takes the inputs of the current position of the player from the memory module. This set of connectors takes the snake's head's 4-bit input from the players. This set of connectors takes the 4-bit input of the snake's head from the players, and this set of connectors takes the 4-bit inputs from the player's oscillator register. Then this set of connectors takes the inputs of ladder length from the player, and this set of inputs takes the 2-bit input from the dice module. And here are some connectors as we can see, and some bypass capacitors which we will need for the ease of the PCB design, that we will show later. Now if we insert if we go inside this child sheet, we will see that at first we deal with the player's current position that we took from the memory module, and then we add the dice's 2-bit input through this first 4-bit full ledger. Then we get the first tentative position from this output, from the output of this first full bit adder. Then we use this comparator to compare with this ladder's bottom position. If the bottom position matches with the first entry position, then we take that output and make it as a common input for these four AND gates. And the other inputs for these four AND gates are the ladder's length that we take from the player initially. If the ladder is bottom position and the player's first entered position are the same, then this wire will give out 1, which will activate these AND gates, and it will just give outputs this whatever we had put into this inputs as the ladder length. Then this adder will add the first entered position of the player with the ladder's length, then we'll get a second entered position. But if the ladder's bottom position does not match with the first entered position of the player from this 4-bit full adder, then this wire will give out 0, which will deactivate all of these 4 AND gates, and then this adder will just act as a follower of the first entered position. So whatever the output is, we can consider that this the output of this second 4-bit full adder is just the second entity position of the player. Then we have to deal with the snake's head position. Now what we can see is that the second entity position goes inside this comparator, which gets compared with the snake's head position that we had taken earlier from the players. And if the output is 1, then as using the previous logic, we will just make the output of this comparator as common input for all of these and 4 AND gates here. And if we take the AND gate here as the output of this AND gates, we will be taken as the input for this for this last 4-bit full adder. Now, what we know is that the snake's length will have to be subtracted from the player's position if the player does reach the snake's head position. Now, so for that purpose, we use these 4 AND NOT gates to invert the inputs of the snake's length so that we can utilize this 4-bit full adder as a subtractor actually. And so if the player, the second entry position does match with the snake's head position, then this output will give out 1, which will enable the subtractor operation of this 4-bit adder. But if it does they do not match, then this output, then this wire will give out 0, deactivating all of these 4 AND gates are giving output as 0, and this 4-bit adder will just act as a follower like the previous adder that we had discussed about. So this is a discussion about the child sheet. Now if we go back to the parent sheet, let's if we go for a demonstration purpose, let's say we have turned on the game. So at first, what the 2 players need to decide is the position of the snake's head and its length, and the ladder's start position and the ladder's length position. So snake's head here is let's say we might give out as 1 1 0 0, and the snake length might be 1 0 1 0. All right. And let's say they have decided that the ladder's start would be 3, which is 0 0 1 1, and the ladder's length, which is 0 1 0 1. All right. Now after a round of play, let's say the player has one of the players has reached, let's say 2. So 0 0 1 0. All right. So it will just give 0 0 1 0. Nothing new about that. But if he or she rolls the dice again and get 1, then the position will become, let's say if we input 1 here, so which is 0 1 in binary, 0 1. So what happens is the player was at 2, and the dice after rolling gave in output as 1. So 2 plus 1 equal to 3, which in binary is 0 0 1 1. So this the player reaches the ladder start position. Now ladder start position, as we can see that it ends at 8, right? So 3 plus 5 is equal to 8. Let's see if the player has indeed reached 8 here. Yes, 0 0 0 1. So which is in binary, it is 8. So this is how it is working. Now one criteria was, if the snake's head position and the ladder's start position are in the same place, then what will happen? And in that case, the ladder's head or the ladder's start position will get priority. So if the player reaches the snake ladder start and the snake set position and simultaneously, then the player will get on the ladder instead of going inside the snake. Now, if we can show that particular demonstration here by let's say here, let's say we give a common place for snake set and ladder start. Let's say 0101. So 0101, sorry 1010, and let's say ladder start we give as 1010. All right. Now we have to make a bit of changes somewhere else as well, because they both are at since they are at 10, 1010, which in decimal is 10. Let's say ladder length we give it as 3, so 0011, 0011. And let's say we give snake's length as let's say 4, which is 0100. All right. Now the player was initially at 3. Let's say after a couple of rounds, one of the players reach 7, which is 0111. All right. And now after rolling the dice, they get 3. So 3 in binary is 1 1. So we give 1 1. Now we know 3. The 3 from dice and the player's current position of 7. 7 plus 3 equal to 10, which is equal to this position of the snake's head and the ladder length as well. Now, according to our previous condition, the player should get on the ladder instead of being eaten by the snake. But does it happen though? Here we have 10, and the ladder length was 3. So 10 plus equal to 13. So the player should reach 13. But does it happen? Yes, it does happen. 1101, which in binary, which in decimal is 13. So the criteria has been met here as well. Now we can conclude that this is a successful logic module, and we can consider it as a successful heart of the game. So yeah, thank you. And this is the PCB layout of the game, and which in 3D visualizer we can see this is the board. So yeah, this is all about the snake ladder logic model. Thank you for being with us.
Here it is the dice module. R1 is the pull-up resistor, and below there is a push button. Here inputs S and R and clock pulse signal, which comes from a 555 timer IC. S and R is the input of debouncing circuit. When we push the button, S takes input as 0 and R takes as 0. The Q then gives us 1. Here signal goes to memory module. Q, and clock pulse passes through an AND gate. The counter of clock pulse activates. In the counter we use 2D flip-flops. By using state diagrams, we find out the logic of dice rolling and made it in the way where we don't get 0 in out 7 segment display. And O0 and O1, this output goes to snake ladder logic module to sum up with the previous output, as dice output is 2 bit, so that we shorted other 2 bits with ground. For PCB, we need to add 1 block and 5 coupling capacitor for 5 ICs. There is 4 conceals, 1 for clock pulse, 2 for dice, and other for signal. Here is our PCB design and its 3D view.
These are high frequency memory clock. Here is the sub-circuit, main sub-circuit. These things are additional things for the PCB layout. Here we have taken the power, 5V power with the in the VCC input, and we are taking the output from here. Let's look at the sub-circuit. Here we used a 555 timer IC to generate the clock pulse. We configured it in the stable mode to generate a continuous clock pulse. Here how we have done it, we connected first we have connected the VCC with the VCC pin and the fourth pin, and then we have shorted the trigger pin with the threshold pin, and we connected the first pin with the ground. And here in between the fifth pin and the ground, we have connected a capacitor of value 0.01 microfarad, and in between the threshold pin and the ground pin we have connected another capacitor of 0.1 microfarad. In between the discharge pin and the threshold pin we have connected a resistor of 10 ohm, and here in between the VCC pin and the discharge pin we have connected a resistor of 11 kilo ohm, and we are taking the output from the third pin. So that is all. And if we want to look at the PCB layout, this is our PCB layout. If we look at the 3D visualizer, this is our visualization of our PCB. Yes. Another thing, to calculate the frequency, we can use this formula. As we did in our project report. Here, this formula. The RA is the 11 kilo ohm, and the RB is 10 ohm, and the C is 0.1 microfarad. So here we get that our frequency is 1.3 on kilohertz. The frequency of our clock pulse is 1.3 on kilohertz approximately. So that is a high frequency. That is all. This is our memory module. First, let's discuss let's see the inputs. This is the new position input. This is the LSB and this is the MSB. It comes from the snake loader logic module, and we get this input. We get the input after calculating all those things. After we release the dice push button, and so this is it, and this is the carry out. You also get this from the snake loader logic module. This is an active low configuration. That's why we put a dash here. We use this input to prevent the overflow of the game. This is a special feature of the game, and this is it. And this is the dice input that comes from the dice module. This is the 1-bit input. This is not the value that we get from the dice module. This is a signal that when we press or push the push button of the dice module, this input gets on. There is a high value, and when the push button is not pressed, it is 0. We use this input to control the memory updation. So it plays a vital role in the memory module. And this is the clock pulse that we get from the high frequency module. Nothing more. And this is the reset input. It is also in active low configuration. That's why you put a dash here. It comes from the reset module. This is the reset input. It comes from the reset module. When it is 0, all the memory gets all the memory resets, and when it is on, nothing happens. And this is the player selector input, which comes from the player selector module. When it is 0, it indicates that we are working with the player on, and when it is on, it indicates that we are working with the player 2. We will update the player 2 position. And this is the signal to PC register output or the input. It goes to the player selector module to help in the auto toggle operation. when on bit of the signal, say when a high value goes to the player selector from here, if this thing is 0, if this input is 0, then it becomes on, and if it is on, then it becomes 0. And this is the player 1's position, this is the player 2 position, this is MSB, this is LSB, and this is MSB, and this is also LSB, and this is MSB, and this is the selected current player position. When the player select is 0, it outputs the player 1's position, and when it is on, it outputs the player 2's position. And now let's see the child sheet. Here it is the memory. It contains the player 1's position, and it contains the player 2 position. Inside this there is a 4-bit register made up with D flip-flops, 4 D flip-flops. Here it is the D0, this is the LSB, and it is MSB. There is the clock. We control this clock to decide when to update the memory. And this is the reset input. When it is 0, the whole thing gets reset. Now same goes for the player 2's position, the same thing. Now see how we control when to update our memory. This is dice on-off sequence detector. It plays a vital role in the memory updation rule. It basically works like this. When we don't press the push button of the dice, it outputs 0, and when we push the dice button, it outputs 0, and when we hold the dice push button, it still gives us 0, but when we release the dice button, it outputs on. That means when we get the dice's value, then we decide, then we tell this memory to update the new position. This is the new position. Yes, and here is player selector. When it is 0, then here the value becomes on, and if the output is on that time, and the carryout is 0, then here is on, then the player on gets updated. And when player selector is 0, this whole thing becomes 0. Then the player 2 don't get updated. And when it is 0, this value here becomes when the player selector is on, this thing here becomes 0. Then the output of the AND gate becomes 0, and nothing happens in the player on's position. The position don't get updated, and when it is on, this player 2 becomes activated and gets updated in the right time. And when carryout is on, when carryout is 0, when carryout is on, this thing becomes 0 here, and the memory don't get updated. Neither of the registers don't get updated. Now here the selected current player positions giver. It is simple. We take input from both of these register. It is the LSB, it is the MSB for player 1 position. This is the LSB, this is the MSB for player 2 position. And this is the player select input that we get from the player selector module, and this is our output. This is the LSB and this is the MSB. Now let's look at the child sheet. This is the player select. When the player selector is 0, this n gets all the n gets output 0, and no matter what these values are, and when it is 0, these things become on, and we get just this values, and we here use the OR gates to combine these for 8 outputs into 4 outputs, because when it is 0, these things become 0, and in this output we just get these values, and when it is 1, we just get these values, the player 2 positions. So this is it. That's how our memory module works. And if we look at the PCB, this edits we made for the PCB. So this is the PCB, and if we want to look the 3D visualizer, this is our 3D visualization. So this is it.
Here it is a reset module. Here it's a push button and it's a pull down register. As we push the button, it supplies 1 in the input. Here we push the button, its output became 0. Here is our internal circuit. When input enters as a 1, the output becomes 0 and LED lighten up. As our project ran on a common anode method, the output became as soon as the circuit activated. The whole game reset and a new game started. Here we push the button, the LED lighten up. It indicates that the game reset. Before PCB drawing, we need to add T block and the coupling capacitor and the console. Here is our PCB design, and it is our 3D view.
The player selector module. The player selector module has 2 inputs and 1 output. The first input raise comes from reset module. The second input signal is received from the memory module, and the output of the player selector module is then sent back to the memory module. In the child sheet, we used a JK flip-flop. We know that if the input of JK flip-flop is J equal to K equal to 1, output will toggle. In this case, we have taken the input of J and K equal to 1 by connecting power. The clock pulse is connected with the input signal. Initially, the memory module sends an input of 0 and the NOT gate inverts it to 1. When the push button in the dice module is pressed, the memory module sends 1 and the NOT gate flips the 1 to 0. As the button is released, the memory module returns to 0 and the NOT gate inverts it back to 1. The JK flip-flop is triggered by a positive edge clock pulse, activating it when the signal transitions from 0 to 1. The output of JK flip-flop is as follows. When Q is equal to 0 and Q prime equal to 1, the red LED will turn on and activating player 1. When Q is equal to 1 and Q prime is equal to 0, the red LED will turn off and the blue LED will turn on, activating player 2. The input race is connected to the reset input of the JK flip-flop. Which is sourced from the reset module. When the reset button is pressed, race receives a 0 input which is passed through a NOT gate and then sent as a 1 to the R input of the JK flip-flop. As a result, the output of the JK flip-flop is set to the reset condition. Here is our PCB of the player selector module, and here is the 3D view of the following PCB.
So this is the winning module, and so first we take the two 4-bit input, each for player 1 and player 2 from the memory module, as you can see here. Then the 4-bit input are sent to a comparator, one for each player in this case. So if we go into the child sheet here, you can see, so yes, there are two comparators here. Those 4-bit input from the memory module, they are compared with the final position for the winning position on the board, which is 15 in decimal or 1111 in binary. So if the input 4-bit is equal to the winner position 4-bit, that is A equal to B, so this output, then the comparator will give out a signal. This is true for both player 1 and player 2. The output is connected with an LED. If we see, yes, here we have LEDs, and if player 1's current position is equal to the current winning position player 1's then winning position, then the player 1's LED will light up. Player 1's LED, here we have used red, and if the player 2's current position is equal to the player winning position, player 2's LED will light up, which is blue in this case. Thus, in this way the winner will be determined. Now one of the players will of course reach 15 first, so there's no chance that both of these LEDs will light up at the same time. So if we give a bit of a demonstration here, let's say player 1 has reached 15, so which is 1111. So yeah, the player 1's it reaches the 15, so it lights up. Player 2 reaches the 15, then 1111, it also lights up as well. So there's this connectors here, there's a terminal block, and then there's two bypass capacitors here which we used for the ease of our PCB design. And here is the PCB, as you can see here, and this is 3D visualizer which is showing the board of the PCB that we just showed here. So yeah, this is how winning module works. Thank you.
We will see how all the modules work together and make the whole game. To do that, we'll first run the simulation and press the push button of the dice module. Now we got 2, so our player on goes from position 1 to position 3 because we have got 2. 1 plus 2 equals 3, and if we press that button again, then we get on, and our player 2 have gone from position 1 to position 2. That's how it's working. If we press it again, so our player on goes from here to here. So that's how it's working. Now let's see how the thing is actually working. Here, when we press the push button, when you release it, a high signal goes from here to the memory module, and and the dice value goes from here to the snake ladder logic module, and the snake ladder logic module calculate the whole thing and generate another position which goes from here to the memory module. And as we have seen previously, this signal goes from here to here, and the clock pulse is always going from here to here, and nothing special. If we go in the child sheet, we see that the dice value is actually crucial value. The dice value, which is determining the dice on of seconds. When we release the dice push button, and then we get a high value from here, which actually tells the register to update the memory. And another thing here, if we actually use the dice, we actually use the out value here also to the signal to player selector module, which we use to toggle the player selector, the player. Now the problem is when it is giving us a high value in the memory is updating it also, we are also using it to change the player selector, the player. So it can happen that we want to update the player on's position, but for the toggling operation, before the updation, we got that here we get that the player becomes on. So the instead of player on, the player 2 gets updated, or it can happen that both of the players get updated with the new position. To solve this problem, we have used a NOT gate, so that as this is the positive edge triggered JK flip-flop. Suppose the signal is going like here, so high and then remains constant and then low. So when it happens like that, the memory gets updated, and then as we have used a NOT gate, so when the signal is 0, normally when we do nothing, the clock is always getting a high value, because the signal normally remains 0, so the clock is getting high value. So when the signal becomes high, then for the NOT, the clock gets a low value, and when the signal again becomes on, there is after the updation of the memory, then our clock again get a high value. It's a high value, so then the player gets toggled. So this is it, and here nothing special. We get the player on. We pass the player on's position to the player on position decoder, and player 2's position to the player 2 position decoder, and the selected current player position to the logic module that is required by the lab manual. And is the snake header, the snake head is the LSB and is the MSB, is the snake length is the LSB, and it is the MSB, and this is the ladder bottom, and this is the ladder ladder length. We get these values from the snake position decoder and the ladder position decoder. This is our switch. So we also pass these things to the board module. So our board modules, the LEDs are connected in the common anode configuration. So when we want to lit up this LED, we just make this thing, we just make this this value 0, and then the LED gets lit up. And when normally this end gets 5 volt value, and so the LED does not get lit up. So that is on. And here the other thing, here the reset module, if we press this button, and the whole the whole game gets reset. This is reset. Also, so there is all. Thank you.